ladies and gentlemen. Here we go. So just to give you a sense of the plan for the day today, I am open to going over homework questions, as many as you would like. I would like to just kind of talk through the cart and pulley lab. I had really hoped to get it graded last night, but that did not happen, and I apologize. But I just want to talk through a couple of the concepts of it to make sure that they make sense so that you can use them moving forward. There are a couple of forces that I want to make sure that we've defined on our force inventory. And then we're going to talk a little bit about the quiz for tomorrow, what's on it. I have a practice problem sheet for you. That's going to be what your actual homework is for tonight. And then I will give you some more practice problems if you would like them from the book. But the practice problem set is what I would encourage you strongly to work on for sure. And so we'll work on this. We've got plenty of things to keep us busy. We will get through as much as we can. And whatever we don't get through in class, you will do outside of class and be ready for a quiz tomorrow. Does that make sense? Because we're going to quiz tomorrow over this material. The practice problem sheet will give you a sense of what you will see on the quiz tomorrow. Does that make sense? Kind of like we did with the vectors. Remember that vectors practice sheet that I gave you with the vectors problems and the projectile problems? And then if you understand how to do that, then you should be able to transfer those skills to another set of problems. Same kind of deal. Does that seem fair? Questions before we go ahead moving forward? All right. So I'm going to look at homework questions. I hope that you have spent some time working on those homework questions. And if you have, and if you have some questions, this is the time to ask. So what you got? Yes, ma'am. For sure. Number 43. So go ahead and get a book out if you don't have one out in front of you. I'm going to turn to page 148. Question 43. Yeah. Let's do it. So question 43, it says a 5-kilogram bucket of water is raised from a well by a rope. So we've talked a little bit about ropes. We haven't talked a lot about them, but we'll figure out what this means. It says if the upward acceleration of the bucket is 3 meters per second squared, find the force exerted by the rope on the bucket. So anytime you look at a forces problem, the very first thing that I want you to do is to draw the thing that's right above the G, which is picture, right? And the kind of picture that we're going to draw for a forces problem is always a specific kind. That would be the, what is it? Freebody diagram. So there's my bucket. You can draw your bucket to look like a bucket or a square or a dot. I don't care. Okay. So we're going to start off, and we're going to make a little note here that this thing we're going to start off with is the Freebody diagram pretty much every single time. Okay. So a free body diagram is a diagram of an object with all of the forces acting on that object. So what forces are acting on that object? Got one? What force is acting, or what object is acting on the bucket?
Force of gravity.
What object is acting on the bucket?
I don't know.
You're so close. What object causes the force of gravity, friends? The earth. The earth pulls down. That is the force of gravity, the thing we call the force of gravity. So I'm going to draw this like this. I'm going to write this as the force of the earth on the bucket. I'm going to put in parentheses that's FG. And labeling that like this is exactly how I want you to do it. You absolutely will get to label a force of the earth on an object tomorrow on the quiz. Probably twice. There you go. All right. What else you got? Any other forces acting on the bucket? Given that the bucket of water is being raised from a well by a rope, it has an upward acceleration, blah, blah, blah. Yeah, what you got?
The force of the rope is upwards.
Yeah. We can extrapolate from the words here that there's got to be a rope and the rope is pulling up. So we're going to write the force of the rope. Now I have a question. If it's accelerating upward, how do you think the force of the rope compares to the force of the earth? It's got to be bigger. So I'm going to draw it a little bit bigger. I'm not going to grade you on your test for having I'm not going to get my ruler out to check. Okay. But it's just kind of a nice thing sometimes to write that down so you get the idea. So this is the force of the rope on the bucket. I'm going to call that a tension force. You can call that an applied force. I'm not going to count it wrong if you call it tension or applied force. It is not a normal force, however, so make sure you don't call it a normal force. The normal force would always be the force of some sort of surface, acting on the object. Okay, so the floor or the chair or the table or whatever. It's got to be a surface, a wall, something like that. So far, so good? Okay. Now it wants the problem asks us to find that force. Let's write down our givens. What else do we know besides this stuff? Take a look at the problem. What else do we know? Stella, you sounded like you were about to say something.
Yeah, then the raising hands and stuff.
Oh, okay. Go, Ben.
Bucket is 5 kilograms.
Okay, so what am I going to write? Equals 5 kilograms. What is it that equals 5 kilograms?
The mass.
The mass of the bucket. So I'm going to go ahead and write M is equal to 5 kilograms. Got something else?
Our upward acceleration equals 3 meters per second squared.
3.0 meters per second squared. Okay? So I've got my picture. I've got my givens. So I've got the P and the G. And I guess I could write the unknown. I kind of implied it there, but I'll write it out here just so that we are being, complete. The next thing that we need are our equations. Or an equation. This unit does not have equations per se that it actually spills out and spits out. You get to figure out the equation. It's like a choose your own adventure, but there is one right answer. Okay? It's an F net equation. So we're going to write F net is equal to, so this is the key. We're going to go through this a bunch today, so I want to make sure it makes sense to you. Once you've got your free body diagram tells you what to write down here. Net means all of them. All of the forces acting. I'm going to go ahead and write a little y there just to remind me that I'm only looking in the y direction. This case, we don't have any forces acting in the x direction, but you will sometimes, so it's probably a good idea to have that just kind of to notice that for now. Okay? What forces are acting in the y direction? The rope and gravity? Yep, I'm going to write those as Ft because I'm lazy. And I've written that as Ft here. And I'm going to write this as Fg. So I'm going to write those down, and then I'm going to say, okay, are either of them going in opposite directions? Does one of them need to be negative? Which one, Ryan?
Fg.
Fg. All right, so I'm going to make that negative Fg. And then I'm also going to know and notice and be aware of the fact that I wrote it out this way before. A equals F net over M. But for our cases here, we really want to say that F net equals, multiply by M on both sides, M times A. So I'm going to set this equal to MA. This right here, friends, is the key to your success in forces problems. You've got your free body diagram. The free body diagram dictates your F net equation. So F net, you're going to write down the forces that are acting, and then you're going to write down equals MA. Does that make sense? Okay. Do we know FT?
No, we don't.
We don't. That's what we're trying to find, right? Do we know FG? I don't have it written here, but can I find it? Because I've got that fancy golden sheet, right? That golden sheet that I have, that you have, and it also is on your equation sheet, on your orange equation sheet if you want to look at it. FG should be listed there. It is. FG equals MG. So I'm going to write this out again. I'm going to say FT plus minus MG is equal to MA. The mass is up there. I can write down my G is 9.8 meters per second squared. I often have students that ask, should it be negative? So here's the funny game, ladies and gentlemen, and you can do it either way, and it does not matter which way you do it. But you want to make sure that this thing here is negative. So if I have a negative sign out here, then I just want to plug in the magnitude here. I just want to plug in the 9.8 because I need this thing to be opposite of this one. FT and FG have to point in opposite directions. Okay? So I know M, I know A, I know M, I know G, I can find FT. Okay? Right now I'm subtracting MG. How do I undo subtracting MG? I'm going to add it on. This is such a good problem. I love it. Add mg to both sides. And then I've got my answer, essentially. ma plus mg. If you want to factor the m out because it makes you happy, you can. I don't care. You can just plug numbers in. That works too. Shall we plug numbers in real quick and double check to make sure things make sense? Yeah. Go ahead and do that. As you're doing that, I do want to make a plug. I noticed when I went over to grab a calculator today that I am like 5 calculators short. So I want you to double check and make sure that you haven't happened to grab one of the calculators that are so convenient to use that I have up here and that it happens to be in your bag instead of in the front. I'm not like upset with you. It's all good. Just make sure it gets back there so that we can share the fun with everybody. Okay? So please, please, please make sure you haven't accidentally grabbed one of my calculators, or if you not accidentally, you on purpose did it, bring it back, please. All right. Did you get a value? FT? So it's 5 kilograms times 3 meters per second squared plus 5 kilograms times 9.8 meters per second squared. Did you get a number, a value, an answer? 15 plus. Comes out really nice. Woo! What do we get? Yeah.
64 newtons.
64 newtons. How are we doing? Okay. This is a lovely problem.
How many of those are you doing?
There are going to be 2 forces problems on the quiz. And then there will be 1 or 2, I haven't decided, like ranking to just kind of make sure you're understanding how to, like kind of the conceptual. So I'm going to give you the review sheet, and the review sheet was modeled after the quiz. So I wrote the quiz and then I wrote the review sheet to look similar. Does that make sense? Yeah. Question?
Can we talk about number 24?
Sure thing. Questions on this one before I move on? So just a reminder, I am recording this. I don't mean that in a bad way. I just mean that if I went too fast or if you want to see it again, it will be up on YouTube tonight so you can watch it again if you need to like watch this over and over. It's all you. Yes, you may. Yeah. All right. You said 24, Isaac. Is that right?
Yeah.
Okay. Let's go up here. 24. Let's take a look. 24 is on the other page. Says a 1.50 kilogram baseball is thrown upward with an initial speed of 20 meters per second. What is the force on the ball when it reaches half of its maximum height? What is the force on the ball when it reaches its peak? Okay. So it wants to know the net force, right? So let's draw a free body diagram. Whenever you're trying to figure out forces, let's draw a free body diagram. So let's draw a baseball. Hey, it looks even like kind of like a baseball. Woohoo! All right. So it's being thrown in the air. Do you want to do halfway up or at the very top first? Halfway up, because that was part of it. You guys are so literal. I love it. All right. So as it's traveling, I don't have a baseball. I do have a frog, so we'll throw the frog in the air. So we're talking about right now, right? When it's like right here, it's going this way. What forces are acting on the baseball frog? Gravity, right? The force of the what? Force of the earth. Anything else acting on the frog? Baseball. It says neglect air resistance. Anything else pulling or pushing on it? Nope. Okay. So F net. We're going to do it anyway. F net, well, it just equals, oops, that was FG, right? Equals FG. That's all you got to do. It doesn't even ask for the acceleration. We could figure it out. But it doesn't ask for the acceleration. It just wants to know the force. So the force is the mass times negative 9.8 meters per second squared. Okay, or you put the negative out in front. Either way it works. And you know the mass because they told us it was whatever it was, 0.150 kilograms. Times negative 9.8. Boom. Does that make sense? Sweet. And then part B says, what is the force on the ball when it reaches the top? Is it going to be different? What's acting on the ball when it gets to the top? Just gravity, just the earth, right? And nothing else. So it's the same darn force. The same darn force acting the same time. It was like something like 1.47 newtons downward. Yeah.
Is it negative or is it positive?
It's going down. Right? Force pulls down. So I call it negative. If you want to be ornery and call down positive, you can. I'm not going to tell anybody, but I wouldn't.
So on a quiz, is it
So if it was on it, so let me read the question what it says. What is the force on the ball? So I would say negative because it's going down. Or you could say 1.47 newtons down, right? Yeah. I'll just leave it there.
Use the acceleration.
Say that again.
How can we use the acceleration?
In number 24? Is that what you're asking about?
Okay, it's velocity.
It's a velocity, yeah. Yeah. It was just there to trip you up a little bit. Yeah, yeah. And I honestly forgot that it was there after I read it out loud. Yeah, yeah. Velocity doesn't matter. It could be going really fast, whatever. I have a question for you. Ready? Okay. You watching? I don't have a baseball, but I have a frog. I'm going to say now, after I've, done things with it, I want you to tell me what the force is on it right now. Just gravity, right? The whole darn time. The Freebody diagram of that frog the entire darn time is what? Just the earth pulling down. That's it. It doesn't feel like it should be, right? Because look at it going. But if we think about it, if we literally think about the acceleration is only going in which direction? Down. Do you remember that? We would do this over and over. Down, 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 down. It's not accelerating in the x direction, so there's no net force in the x direction. It's only accelerating in the y direction because the earth is pulling down on it in the y direction. That's it. That is it. Nothing else is acting. Yeah. Other questions on the homework? Anything else you want to talk about? No? Okay. If you change your mind, let me know. All right. Let's see what else is next on our list to do. So we did that. All right, cart and pulley lab follow-up. So maybe in your notes, I just want you to write down a couple of things here just based on what we observed. Again, I don't have your labs to give you back, but I just want to make sure that you're feeling okay about this. And maybe just make a couple notes in your notes. So I'm just gonna write it right here. But if you want to write this in your notes, this was the cart and pulley lab. You write down cart and pulley lab. Some of you graphed acceleration versus mass of the car. And some of you graphed acceleration versus the force on the car. Does that make sense? Or cart, I suppose. So this was if you were changing the washers. This is if you were changing the mass of the cart. Who did the force on the cart? Were you a force on the cart person? Yeah? Malik, do you remember what your graph looked like for the force on the cart? It was like a line. Did it have a positive slope or a negative slope? Positive slope. So it looked something, hi ladies, something like this. Oops. Something like that-ish. Okay. So I want you to write this down. I want you to write this down so that you know this, so you understand this, so that you're internalizing this information. So the force on the cart, as the force increased, the acceleration increased. As the force goes up, the acceleration went up. That's saying that acceleration is dependent on net force. As one goes up, the other goes up. I just repeated myself 3 times. Hopefully it made sense. Who is in charge of changing the mass of the cart? It's just Stella. Anybody else? A few others up there? Yeah. What did it look like, Jordan?
It's like
It went down. So there was some sort of relationship where as one went up, the other one went down. Yeah. And it's a little hard to tell because we like lines. We like lines a lot. And I think most of you only took like 4, maybe 5 data points. So it's kind of hard to see. But really, it should look something like that. Okay. So it may have looked kind of like it was a line, except there was one point that was out of whack or something. But really, that's what it should look like. We can say as the mass goes up, what happened to the acceleration? It goes down. Okay. The reason, go ahead.
how come why is it not just like straight line?
Why is it not linear?
Yeah.
Because of the short answer is because of the relationship between them. It's because it's inversely proportional. So it's not a one-to-one relationship. The relationship literally is that the product of the mass and the acceleration is constant. I'll show you what that means in just a second. Is that okay? So the reason we did this lab was not to discover something new, but it was to verify something that I tried to, get you to believe earlier. I want to show you where it may have existed here. Let's see if we can find it. Where did it exist? We were doing, I think this guy, nope, this one here. Here we go. So we did this a long time ago, right? We did this a long time ago. And then, we said this. We said that if the mass goes up, the acceleration goes down. We talked about this with the balls, right? If I was rolling 2 balls, I had the bowling ball and the basketball, right? That if I increased the mass, the acceleration was going to go down. I kind of convinced you of it, kind of in a thought experiment. But the reason we did the cart and pulley lab was to actually show that it really happens. That as the mass goes up, the acceleration goes down. And then, remember I gave you that other thought experiment to say, if you were pushing that bowling ball versus my 3-year-old daughter pushing that bowling ball, which one of you has a bigger force? Who's going to play a bigger force? Me, I'm totally going to do it, yeah! Because my 3-year-old and is, she's cool, but she doesn't have that much force, right? So you have more force, which means you're going to have a bigger acceleration on that ball, right? Again, I kind of convinced you of that. We kind of thought about it as a thought experiment, but the lab that we did, really, the purpose of it was to show you that actually is true. So if you look at the acceleration, the acceleration is dependent on force. And as F net goes up, A goes up, okay? That's like a y equals mx plus b sort of thing. That looks like a line. You with me there? Looks like a line. This is my A equals some sort of slope times the force. Yeah. So there's some sort of force here. A and F are proportional, okay? As M goes up, though, A goes down, which means that M needs to be in the denominator. It needs to be underneath, okay? So the game is, here, Isaac, this is what I was going to show you, is if you multiply M to the other side, you've got A times M. The constant here is that they're all the same force. So every single time that we ran this, if you were the mass, who did mass of the cart? Yeah, you guys did. So, Monse, when you did this, did you change the number of washers that were pulling down? No. So you had the same force every time, but the mass changed, and that means the acceleration changed. Does that kind of make sense? That's where it really comes from. So this is, in mathematics terms, this is called a hyperbola, and literally a hyperbola you can get if you multiply 2 numbers together and keep it constant. Does that make sense? Yeah, it's kind of cute. But anyway, that was the whole reason we did this lab. Part of that was also just to collect data and, do that lab stuff and get your hands in there. But this is really what we were trying to show. So hopefully you saw that. That's my goal. That's what I wanted, because that's going to lead us to Newton's first and second law. We good? Do you remember Newton's first and second law? Sure I do. Yeah, it's this thing right here. If F net is 0, then A is 0. And if F net isn't 0, then A isn't 0. That's it. That's it, right? And if F net isn't 0, then A equals F net over M. That's what we showed. That's what we showed. All right. We need to do 2 more things. I want to clean up our force inventory a little bit. Can you pull out that golden sheet that you have that looks like this, I think? Tell me if I'm wrong. Maybe I don't know if I have your classes or the other classes. So I want to make sure that I'm on the right track here. Did we had gravity written down? Is that right? And we had the normal force written down? Did we also have applied force, or was this my other class? We're okay? Awesome. So the applied force comes from a person or a rope. It's going to be something that's given to you. So we know that one. Okay. There are 2 others that one other one that I actually want to write down here, just so that we're clear. Well, but I want to do the applied force. One more thing to the applied force. And that is, I just wanted to draw the picture. So the thing that's important to know about an applied force or a tension force is that you can apply the force in any direction, okay, including at funny angles. So it isn't always going to be this way, but it could be up like this. And the important thing to remember there is that then I would need to break it into an X and a Y part, okay? So I just want you to remember that that is something that could happen. Yeah. There will be. Mm-hmm. Yep. So we'll go through it in just a little bit. Yeah, that's my plan in the next few minutes. Yep. Yeah. So yes, there will be a problem where you will need to break your force into components, into X and Y pieces, okay? Which is just like you did on the vectors stuff. And I've talked to lots of you about how to do that. So hopefully that's making sense. We're going to do it again today. And if you have questions, if you have issues, then you're going to let me know. We'll figure it out, okay? Well, because I want you to know how to do it. But yes, there will be one like that. There's one more force that I want to put on your list as well. And that's the force of friction. And we are going to investigate friction and understand friction much more clearly in a couple of days. We're going to spend some time on Friday and Monday really digging into friction. But I want to just acknowledge that it exists, okay? And remind you kind of big picture of how it might interact with things. So what is friction? Do you know? Your 3rd grade teacher did this, right? My 3rd grade teacher was the one that, like, I remember distinctly, like, sitting in Mrs. Fox's room, and we're going to do science now, kids. And then she was like, this, and, like, we all did that, and we all thought it was so exciting. We were like, oh, my God, it's friction. What is friction? So it's 2 objects interacting, right? Rubbing against each other, okay? They often cause, what did you say? Resistance, yeah, or some sort of opposing motion. Yeah. So the object that's pulling or pushing is a surface acting on the object, okay? So one hand against another. If you think about friction in terms of like pushing something, like a box against the floor, okay? It is the surface that's pulling or pushing. Now, some of you are like, wait a second. I wrote surface up here for the normal force. Say, yes, you did. It's weird. There are 2 parts to that surface force. The surface pushes perpendicular to the surface. That's the normal force. It also pushes, opposite of perpendicular would be parallel. It's also going to push, the direction here is parallel. And the other piece to the direction that I want to add is that it always opposes motion. It always opposes motion. So if I'm sliding a box this way, friction is acting which way? That way. If I start sliding the box this way, then friction is going to start acting that way. It can switch. What? It's kind of weird. But yes, you want to know that it's always opposing motion. The magnitude of it, we will get back to later this week / early next week. So we're going to leave that one blank for right now. Is it able to cause acceleration? You bet. Yep, it can slow things down. But it doesn't have to. The other time that we kind of like friction is because friction can keep something at a constant speed. So if I'm pushing on something like a chair, I'm not going to get that chair up because I don't want to waste time, but if I'm pushing on a chair and I'm moving it at a constant speed means how much acceleration? No acceleration, right? I'm applying a force this way, so that means that friction is pushing which way? The other way, and it's pushing the same amount because it has to add up to 0 so that the acceleration is 0. Are you with me there? Okay, so absolutely it can cause acceleration, but I want you to notice that this doesn't mean that it does cause acceleration. Okay, it can, kind of like any of these, but it doesn't automatically cause acceleration. The diagram for it, so here's my frog. I'm going to give it some little lines of motion. Look at it, it's going. If the frog is going this way, which way is friction pushing? The other direction, right? The other direction, it's going this way. So far, so good? Is that all right? Okay. Again, we'll talk about how to break it up in a little bit, but for today and for tomorrow, all you need to know is that it exists, that it's a surface on an object, and that it will act opposing motion. How we doing? We all right? All right. So what we're going to do now is work on some problems. I'm going to give you this review sheet. We're going to get through as much of it as we can. And whatever we don't get done now, you will work on later. Does that sound okay? So, Isaac, why don't you hand some out over on this side? I'll hand some out on this side. We'll meet in the middle. Two are some problems, and I put them up on. I will put them up on. Mr. Oswald sent you an email, right? Yeah, he said, I budged! Like, yeah.
He obviously didn't think physics was important.
I know. Yeah, I saw that. I almost sent him a snarky message back, but then I realized he was giving blood, so I didn't want to, upset him. Did you guys get cookies?
Yeah.
Good. My favorite sticker, like from giving blood, is I did it for the cookie. Yeah, it's pretty funny. All right. In the interest of time, I want to spend a little bit of time with you working on the problems, but I want to strongly recommend that you look at the ranking tasks today, and I will plan to put up solutions to this today, okay? That said, I do have to run right after school to go to my daughter's parent-teacher conferences, so if you are looking for it tonight and it's not there, just send me a quick email and say, hey, Ms. Carbeling, do you have the solutions? I'd appreciate it, thanks. And then I'll put them up as soon as I can. Does that make sense? I know that when I leave this space, sometimes I forget what I'm doing, okay? So I don't want you to be mad at me, just know that life is busy. Before we do that problem, though, let's take a look here. This is where I really want you to focus for just a moment here. If there is no net force acting on an object, then the object's acceleration is? Yay! Awesome. Make sure you write that down. Don't forget that. I'm going to skip the conceptual, but I will put solutions up so you can see it later. I want to look at the quantitative. I wanted to get to this one because Stella was just asking about it, about breaking something down into the X and Y components, okay? While at the grocery store, Sweetums is the big, like, guy in the Muppets. I think he's pretty hilarious, is pushing around a 47-kilogram shopping cart. He applies a force of 27 newtons at an angle of 19 degrees below the horizontal, and the cart moves at a constant speed. Okay? Draw a free body diagram of the situation, write out the F-net equations, determine the normal force, and determine the frictional force acting. This is exactly what it's going to look like on the quiz tomorrow, okay? Like I literally copied and pasted this from the quiz and put it in here. I wrote a different question for you, but it's the same 4 tasks. Okay, so no surprises there. All right? So, shall we start by drawing a free body diagram? Yes, that sounds great. All right, so draw yourself a cart. And then tell me, my friends, what forces are acting on that cart? Go.
Gravity,
Indeed. Which way does that one go? Straight down. You got it. Fantastic. Yes, ma'am. Force of the floor on the cart upwards. Awesome. Okay. Anything else acting on my cart?
Yes. The applied force.
His applied force, right? Sweetum's force on the cart. So this one is a little bit funny because it says it's being below the horizontal. So how do I interpret that? I'm going to draw horizontal. Doop, 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 doop. Horizontal means like the horizon is going to be a flat line like this. And then I'm going to draw the angle down from that. So to be clear, it would be like Sweetums is standing over here, right here, like whatever, like this is him. Oops, that's not very good because then he's like the same size as the cart. Oops, I just keep making really big heads. Let me try that again. There, now he's big. There he goes. So he's pushing down like this. I must have some wheels on it or something like that. Okay. He's pushing down like this. So his force is going down into the cart, but I want the force to actually come from the cart so that I can show where the cart would be going. Does that make sense? So I'm going to draw the force down here on the right-hand side, even though he's standing over in the way I've drawn it on the left-hand side. So here's my force. Oops. Come on, little thing. There we go. So that's the force of Sweetums on the cart. That's an applied force. Okay. So there's my free body diagram. Anything else acting? Friction. How do you know friction is acting? He's pushing against the surface. And what else does it say? Below the horizontal, and the cart moves at a constant speed. There's zero acceleration, and if there's zero acceleration, then I've got to have friction, right? I've got to have it, which means it's got to be opposing the motion. Which way does that go then? That way, right? So I'm going to erase Sweetums here. See you later, buddy. So there's got to be a force going this way. The force of the surface on the cart, FF. And again, the reason that I know that is because it says that it's moving at constant speed, which means that A has to equal 0, which means that F net has to equal 0 in both the X and the Y directions. And if we look at it without this pink force, there's going to be a net force in the X direction, isn't there? So that can't be at all. There's got to be friction. And because part D says determine the frictional force. So it kind of gives you a hint as well. Okay. What do we do now? We're done with part A. We drew a picture.
You did these. It's just right the givens.
Let's write the givens. That sounds like a good plan. Let's write out some givens. When in doubt, write out givens, right? That's a good plan. What do we know? What's something we know? Mass. The mass of the cart, 47 kilograms. What else do we know? Force. The applied force, the force of Sweetums is 27 newtons at 19 degrees. Blah, blah, blah. But we've got that kind of drawn. I'm going to put the 19 in there. Anything else we know? We do know the acceleration is 0. You can totally put that in there. Acceleration in the X is 0. Acceleration in the Y is 0. I'm going to go ahead and write down G as 9.8 meters per second squared, because we'll probably need that. All right, so we got our picture. We got our givens. Our unknowns, one is the normal force, Fn, and one is the frictional force, FF. All right, GU, PU, and G are done. What's next? It's big and green up there. Yeah, you can say it with confidence. For sure, we need to write our equations. And part B says what kind of equations we need to write, doesn't it? Part B says write out F-net equations. Okay, we can totally do that. Let's write out our F-net equations. I'm going to write out our F-net. There are two of them. F-net in the Y and F-net in the X. Does anybody have a preference? Which one do you want to do first? Okay, let's do it. What things are acting in the Y direction? The Earth, gravity, Fg, right? For sure. What else is acting in the Y direction? Normal force? What else is acting in the Y direction? Some of his applied force, isn't it? For sure. I'm going to zoom this in for a second. Whoa! And take a look at that applied force. It's down at an angle, you guys. I'm going to break it into two pieces, one that goes this way and one that goes this way. You ready? Here we go. Wahoo! FA in the X direction. FA in the Y direction. Hey, this looks like something I've done before. Looks like something you've done before too. Yeah, you can, yes, just go. Yeah. What do we got, friends? How do we do this? Can you do this? The short answer is yes. FAX is the adjacent side, isn't it? So if you need your equation sheet, get it out. You got the adjacent side, you got the hypotenuse. Which trig function is that? It is. No. Don't agree with that.
Wait.
Adjacent and hypotenuse?
Cosine.
Cosine. It's okay. It's okay. I do it too. Cosine is adjacent over hypotenuse. So that means I'm going to just translate that fast to say that that's FAX is equal to FA cosine theta. Can we handle that? Is that okay? If that doesn't make sense and you want to come hang out with me during Liberty time, I'll be here. I'm happy to write you a pass. We can do it together. It'll be great. Let's do it. Let's learn it. FAY. That's the that's the hypotenuse. Let me try that again. That is the opposite side. Now I can speak with authority. That is the opposite side. Opposite and hypotenuse. Which trig function do I want there, friends?
Sine.
Yeah. Indeed. We know that the sine is opposite over hypotenuse. So we can say that FAY, this is getting a little crowded, I apologize, is equal to FA times the sine of theta. Am I okay there? Did I screw something up? It's always possible. We okay? I'm going to zoom out for a minute. So I'm going to add FAY here. What do they have to add up to? To what? 0!
Wait, you need to add up to 0 because it ain't going up and down. Yeah.
It's not accelerating.
Gotcha.
Not accelerating. Constant speed, not accelerating. F net equals 0. Yeah. Is that okay? Yes. Yes. Are any of these negative?
Yeah, our FG is going to be negative.
FG is negative. Anything else negative?
Yes. Our FYY.
FAY is negative in this case as well. Let's mark them. negative FG, negative FAY. Solve it for FN. It can be done?
It can be done.
Okay. Looking at the clock. I'm going to leave that for you to do, and I'm going to write down the FNet and the X direction one, okay? All right, here we go. FNet in the X direction. Here it comes. We've got FAX. I'm giving you that one. What else is acting in the X direction, friends? Force of friction. And how do those work? What do they have to add up to? 0, because it's not changing speed, which means it's not accelerating, which means F net equals 0. Are either of these ones negative?
Yes.
One of them has to be, right? If you're adding them up to 0, if you got two numbers, you add them up to 0, one's got to be negative. Which one? You want FF? Let's make it negative. Okay. You know that FAX is FA cosine theta, so you know the FA, you know the cosine of theta, so you can find FF. How are we doing? Are we okay? Do you want to plug in some numbers and figure them out? Do it. Do it. We've got like 2 minutes. That's a lot of time. I'll write some stuff down too, but what I don't want you to do right now is to turn your brains off. You've got 2 minutes, 2 minutes of physics time. Do it. Yeah.
Why is the FAY?
Because it's pointing downward.
So how would I know when I'm looking at it
To make it downward? Because the question says below the horizontal.
Oh.
That's a really good question. I'm glad you asked that. Did you guys all catch that question? Ryan just had a really good question. He said, how do I know that the FA should point down? And it's because it says below the horizontal. If on a test question tomorrow, it said push blah, blah, blah above the horizontal, then you would know that it's going up this way, right? Okay.
We think about slope.
What's that? You think about slope. It makes sense. Yes.
So FAY, yeah.
Okay. So I will post answers to this on Canvas. You are responsible for this material, ladies and gentlemen. So make sure that you know it. I'll see you tomorrow.